Hello, everyone. I'm Mohammad KESHAVARZI. I'm a PhD candidate at the University of California, Berkeley. Today, it's a pleasure to be with you, and I wanted to talk about my research about spatial computing with generative design. So I hold a joint appointment as a PhD student at UC Berkeley, one in the architecture department at the XR lab, and also at the FHL Life Center, which is in the Department of Electrical Engineering and Computer Science. I'm a former generative design software engineer at Autodesk, and I've been also working in the architectural field as an assistant architect and new wave architecture, coming with a background of architectural engineering from the University of Tehran. So today, I really want to emphasize on what I think would be the spatial problems on our next generation computing platforms. So we're all excited about AR, VR, especially for us architects and people that have been involved in the building environment and spatial design communities. And that's because AR, VR experiences allow us to embody space within our generative computing workflows. Not only in games, but we also have applications in interior design, architectural renderings, and virtual walkthroughs. Another thing that personally really excites me is the fact that we can share our space through telepresence meetings. However, all of these different applications require us to basically generate the whole experiences within our surrounding environments. And our surrounding environments come with a lot of diversity in their geometrical and functional properties. So a content developer or a person that basically wants to generate those experiences for an AR, VR experience would either need to know all the spaces that it wants to design for, or basically is pretty much in the dark for how its design experiences would work within different environments. We had this problem before, a similar problem in 2D devices, which a content developer, say a web application developer, is not able to know that whether the target user will be using a mobile, tablet, or desktop device. But the idea of responsive design has basically helped a lot of application developers to basically generate one set of content, and the system would basically contextualize it based on different sizes and devices. However, as you know, 3D environments, our surrounding 3D environments are not as simple as a 2D screen, and they're not a simple black box, but come with obstacles and a lot of geometrical attributes. They also come with semantics, which, as you see over here, is just a mesh overlay. Our environment holds different properties in terms of what they are in terms of their functionalities. In addition to the problem that a content developer of AR, VR space won't be able to generate a specific solution for all environments, there's also a problem in the applications of telepresence when people want to talk and collaborate together within each other's spaces, on the fact that they are not aware of each other's spaces and they don't know how to align and basically calibrate each other's spaces together. So the problem of spatial computing with these spatial limitations is really interesting to look from an architect's point of view, and whether the workflows we've used in computational design and architecture can help. And we've all have heard of the term generative design in architecture. And just to give you a brief, generative design is basically a paradigm shift for a lot of designers from designing a solution to coming up with workflows to generate a solution space. And using various methods and performance-based optimizations, we basically come up with a way to narrow down that solution space to a handful of solutions, inspect them, and basically come up with one solution of our design. Here is an example of my work at University of Tehran a few years ago of generating a 100-unit residential complex. By coming up with specific algorithms, I generated the blocks and overall geometrical properties for this residential complex. And taking the solution space through some specific optimization workflows, I was able to narrow down to a handful of designs and basically then come up with a way to generate one single solution. So the main question is, how can generative design benefit spatial computing workflows? And I'm going to talk about this question in two of my research directions happening at UC Berkeley as part of my PhD. The first is about content augmentation, the idea of a developer basically coming up with a way to generate a solution that can work with various environments. And the other one is about coming up with mutual spaces and fixing the problem of calibrating mutual space. So let's talk about content augmentation. Just to give you a quick preview of what I'm going to talk in the next few minutes, the idea is if we have a target scene and we have some specific objects with some specific functionalities to be augmented, can we come up with a way to find the best probable placements for these objects so they can merge with, given their geometrical and topological properties with other objects as well. So let's open the problem a little more. Here is a space, a living room space. On the left, you see a top view. On the right is perspective. And say we want to add a sofa to this space using augmented reality or virtual reality workflow. This sofa can be basically generated anywhere in theory, right? But we have two problems coming up. One, the sofa might collide geometrically with other objects in the scene. On the left, you see a conflicting placement. Or the sofa may be placed in a place that doesn't seem plausible and doesn't have any plausible relationships with other objects in the scene. So the way we look at this problem is, can we come up with another representation of the scene? And that's when we use spatial scene graphs that have been recently used in a lot of computer vision applications. So if we have a scene, we represent it, basically, we represent the objects as nodes, and we represent the relationships between these objects, relationships such as their positional, orientational relationships with each other in the room as edges of this spatial scene graph. And when we start generating different possible positions for the augmented objects, we translate them to a spatial scene graph. And the goal is to understand which spatial scene graph would be the plausible and most likely spatial scene graph within the whole set of generated solutions. The question is, how do we calculate this? Well, we learn from previous scenes. We call it a knowledge model, or basically learning a model from previous plausible scenes. And over here you see when we extract the spatial scene graph from them, we're able to train our model and use a KDE positional and orientational inferencing method to understand what's the best possible position for our augmented objects. So here you can see some results. Here is a bedroom. We want to add a bed to our bedroom, and we plot here the probability map of our system. The darker the color, the higher probability the object can be placed over there. And here is an orientational probability map. And as you see, the plausible position of the bed within the environment. Here are some other examples of our work. On the top is the target scene, and the two below rows are basically our augmentation of different furniture within the scenes. We can also have a multi-object placement for our system. Say we have a room, we want to add a bed, a storage, and a sofa. And here you see the probability maps similar to the previous results I showed you. And when we compare our system with the ground truth, we do see some differences, but the differences do not navigate us away from the plausibility of the scene. Here's some other examples of multi-object placements. In some scenes we see are pretty similar to the ground truth. And in some scenes we even add additional objects, and they're completely plausible and contextualized. The whole idea, again, is for contextual placement for augmented reality and virtual reality. So I'm going to show you the application we developed here as augmented reality application. So the first part of the video shows if these objects were to be placed manually, somewhat as you see in current AR furniture applications. The user basically chooses the object and adds the object and then has to spend the time to move and contextualize them within the scene. Here is our system, our scene gen system. It generates a probability map for each object. The users can then navigate and basically modify the scenes after the placement. Okay, so we talked about content augmentation in spatial computing applications using generative design. Let's talk a little bit about the problem of mutual space. And just to give some thoughts about the motivation of this problem from my personal experience was basically after seeing this video of the Microsoft Holoportation project. What was really touching for me is the fact that Shahram Izadi, the presenter, actually steps back over here to enable his daughter to move. And this was very touching for the fact that how telepresence in future spatial computing experiences can be really important for our human social experience. But when we take a pretty much closer look to this scene over here, which on the main scene, you see where the presenter is located, and on the top left, you see where the virtual hologram is being captured. Both spaces come with pretty much large open spaces, and they're also calibrated with each other beforehand. And these 2 points are pretty hard to get when we're having very casual virtual meeting talks together. So if you were supposed to calibrate your space and have a very open space for all the meetings you have, it's going to be pretty much problematic, especially for scenes and participants that you don't know. Another problem is the fact that geometrical and line of sight conflicts may happen. I'll try to illustrate this with an example. So over here you have user A, user B, and user C. In user A room, when we augment user B and C, if we keep the same relationships between the users, we're not able to see the other participants. That means user A and user C in user B's office, because the office is basically smaller. And in user C's room, you might have geometrical conflicts. So you might ask, Mohammed, why don't we just force position the people? Well, the problem comes of a line of sight conflict, which means in some cases, one user may be willing to talk to another, and in the other scenes, you might see a whole different line of sight, basically maybe looking at the wall here and see in user's B part, or even looking at another person. So how do we address this challenge? In our paper, we developed a method to locate the maximal mutual space. And this basically comes from extracting the semantics of the spaces and coming up with a transformation function for the open spaces to generate a maximum mutual space. Now, if we look at this problem through the fact that we can enable sittable spaces for users to also interact and sit within, we would have a much larger mutual space. So in essence, if each of the users of these rooms sit within the blue mutual space, they are able to hold a plausible meeting without any geometrical and line of sight conflicts. Of course, like many generative models, we use meta-heuristic optimizations. And as you see, after going through multiple generations, we can have a maximum mutual space calculated. Now, the question comes what if the users need more mutual space? Well, we had an idea on this that, okay, can we start rearranging the furniture that the mutual space goes up while the effort comes down? And by effort, I mean, if we have our original layout, if we move a bed, the effort is going to be much more than just moving a chair. So moving a chair would be preferable. So here is an example of our optimization definition. So we have 3 rooms, and then we calculate the open spaces and also the mutual spaces using the first system of finding the mutual spaces. And then we start generating multi-objective optimization of the goals of basically minimizing the effort and increasing the area. So in each step, you have 10% of additional mutual space area while basically finding the minimum effort to do so. And here you see the initial setting and the furniture rearrangement, which you have something along the lines of 70% more mutual space, while knowing the effort to do so is possibly the most minimum you can get. Here's the HoloLens visualization of our work. We captured our lab, Corey Hall, at Berkeley, and we started extracting the semantics and calculating the mutual spaces. Over here, you see the mutual spaces in blue, the sandable spaces, non-sandables in green and red, respectively. Future steps of our work, we definitely want to encourage more users to use our system and definitely experiment and study how they work with it. Of course, having cross-platform integration between mobile standalone devices would be something we're looking for the future. And also, there's a lot of literature in robust floor planning methods that we can use. With this, I want to end my presentation. Thank you all for listening through it. I really hope to meet you all in person very, very soon. Thank you very much. Bye-bye.